This is where we're going to come up with a lot of our ideas. So 7.2 is all about graphs of rational functions, and that's exactly what you saw yesterday. So you remember how most of the graphs that we deal with on a daily basis, or most of the things that we do, are things that have a general type of form, right? They have like x squared plus something, or like it's the absolute value of x, or 3x plus 2, or whatever. It's just a general form. These graphs don't really have a general form. They have a numerator and they have a denominator, and then they come with a set of rules that you have to pay attention to. All right? So as you're dealing with these sets of rules and these ideas, just make sure you know how to find the important things, because you can actually find them very, very quickly and very, very easily if you understand the rules. Okay? So I've actually put together the graph so that we can see what it looks like for, it was like the bottom left question. Now that being said, we should be able to draw quite a few conclusions from what we see here. Okay? So I'm going to show you what I would do if it was my calculator trying to figure some things out. I don't know if you guys like this feature or not at all, but one of my favorite features on the calculator is the trace button, because that puts the cursor actually on the graph, and then I can move left and right however much I want, and that takes me exactly where I need to go on the graph. It doesn't move anything else around. I think there's a way that you can, I don't really know how. Can you just move around? I don't know how to get out of the trace function now. But some people yesterday were using a cursor, and they were moving the cursor around to try to make predictions, which is fine. You just move it without the trace button? Okay. So I like the trace button more because it allows me to just kind of jump around. If I want to figure out what happens when x equals 5, I'm going to hit the 5 button, and then I can move on. Okay? So it lets you pick out what values you want to deal with. Now, as I look at this, I should be able to make some form of conclusion about this picture here. Okay? The thing that I think a lot of people are struggling with, because the first question it asked you to look for was holes, and I don't think that that was necessarily the first thing that you should have looked for. The first thing that you should have looked for on the graph was where the vertical asymptote was. Every single person should be comfortable finding a vertical asymptote, because it's just where the line is going to continue going this way, and then it's going to hit a line, and it's basically just going to go straight at that line. Or it's going to go up, and it's going to continue going straight at that line. So basically, it's something that we're putting an imaginary dotted line or whatever at some point that makes it look like it's not going to touch. If I go way over here, that line looks pretty darn close, right? So that line looks pretty close. If I go this way, that line looks pretty close. If I'm right here, it looks like it's going to touch. If I split the difference in between the two, that looks like it's a pretty good guess that that is where the asymptote is going to be. That's something that you can observe. That's something that you can see right away, right? So it tells me that I think there would be an asymptote at -4. If you want to confirm that, if you're in your trace feature, just hit -4. And then if you get nothing, then you're correct. Because if you go to -4 and there is no value, that means that your graph will literally never touch the line -4 ever. That's what we wanted to see. Okay, that's just an observation about the graph. Now, the next thing you should have looked for was the holes. In order to find the holes, we would go through and we would look at our table. And if you're looking at the table, you're looking for errors on the table, right? So you're looking to see where the errors are located. I obviously have an error at -4 because that's where my vertical asymptote was. And I don't know what -2 is. So -2, I just look back at my graph. So when I look back at my graph, I look at -2. -2 is a normal looking thing, right? It looks normal. Some of your calculators are super nice and it'll actually show you a little gap right there. But that means that -2 will not work for this function. There is no value for -2. If you type in -2, if you type in -2 in the trace function, it will show you that there is no value for y. It means that nothing exists. Okay, it's a gap. And the reason that it's a gap is because it's undefined. It would end up making the denominator 0, and that's no good. All right? So hopefully those two things make sense. You can't have a vertical asymptote that's the same thing as the hole. The conversations that I was hearing yesterday while you guys were working kind of started to swing around this stuff. So that's good. I just wanted to confirm. Yeah.
So like when we did the first practice SAT, one of the questions was about a graph being undefined. Would that be like finding the holes?
Yes, that's exactly it. Yep. So what Olivia just said is a graph was undefined in a certain area, and the reason that it's undefined is for one of two reasons. One, that it's a vertical asymptote, or two, that it has a hole there. And regardless of what it is, it doesn't matter what's happening. The reason that it's undefined is because the denominator of the function is 0. And it's kind of like me saying, I have 0 cookies in my hand. Someone come on up and grab a cookie. It's not possible, right? If I don't have anything, I can't divide nothing equally. So if you have 0 in the denominator of a fraction, that instantly means that it's undefined and can't work. So if anything ever asks you why something is undefined, it's because the denominator is 0 for whatever that value is, all right? So the last thing that we asked to look for was either the diagonal asymptote or the horizontal asymptote. And again, I like to do the same kind of thing where I put a guess out there, and it looks like my guess is somewhere like between 1 and 2 maybe. And then I'm just probably gonna guess, I don't know, 1, because it looks like 2 is maybe a little bit closer on the top than it is on the bottom, and it looks like 1 might split it a little bit more evenly. So I would guess that maybe the horizontal asymptote for this one is at 1. Now there's a way that you can check that too. This is kind of tough, but this is what we're talking about in calculus right now, because this is introducing the idea of a limit. It's saying as we approach a certain line, what's happening to the graph. So again, if I go to this trace feature and I type in like 10, notice it takes me to 0.5. I can keep going this direction and notice how my y value continues to grow. My y value is going to get to a point, but it's growing very, very slowly, right? I wonder if it'll let me do like 30. Go away. Do that. So it's just showing you that it's growing at a rate that's very, very slow. And the more you go to the right, the slower that growth gets. But you can see that it's still growing. Now at this point, I'm only at 23, and I've grown like 0.05 for a y value. So that's not really going to do anything for me. Okay. You can also check it from the other way. So it looks like it's getting kind of close to 1, but it's going there very, very slowly. So 1 is probably a good guess. It's going to take 1 billion years for you to get above 1. You can do the same kind of thing going the other direction. So if I go the other direction, so let's say I'm at -5. -5 is at 8, and then look how quickly it goes down. It went from 8 to 7 to 6 to 5. Now we're at 4.5. Now 4. It's going very, very quickly that it's shrinking, but then all of a sudden it starts to slow way, 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 way down, right? I went from 8 to 7 to 6 in 3 clicks, and now I'm going like 1/100th of a time every single time I decrease as it gets closer to 1. So that means that that graph probably is never going to reach 1. So as you start to look at these graphs, be able to interpret what's happening with them. And if you can't interpret, then just try to use your calculator and play around with the functions on your calculator to try and figure out what's actually happening. Okay? That's what I wanted you to see yesterday. That's what I wanted you to try to understand. Now, the big part of yesterday was mainly about the conclusions that you could have drawn at the end, where it asked you, where did the holes exist? It asked you, where did the vertical asymptotes exist? And then it asked you, where did the horizontal asymptotes exist? And I tried to give you some hints along the way. All right? So I'm going to see if anyone actually remembered what was going on. And I'm going to write the first 2 things that you had for an equation yesterday. So the first one was y equals x plus 5 over x squared plus 4x minus 5. And then the factored form was x plus 5 over x plus 5 times x minus 1. Does anyone remember where the holes were located? Or does anyone remember why there were holes in them? Yes. So a hole for this one was -5. And why was that hole -5? Or how can I figure that out, I guess, without having to graph anything? You got it? Good.
I said because there was a +5 on both sides of the fraction.
Okay. So we're saying that the holes exist because of this. That's exactly what happens. Right now, my function is undefined at -5. Because if I were to plug in -5 right here, -5 plus 5 is 0. 0 times, anything is 0. I can't have 0 on the bottom of my fraction. But technically, if I wanted to, I could cancel this, right? If I really wanted to, I could cancel this and I could simplify the equation. If you were to simplify the equation, you actually kind of change the equation because you're getting rid of this problem spot. So instead of canceling the whole thing, we get rid of the problem spot by there being a hole there. It just gets rid of the one problem spot without ruining the rest of the entire equation. So if we say that there's a hole at -5, that means that my graph will look completely normal. I don't remember what it looked like. My graph will look completely normal, but at -5, it's just saying that spot doesn't exist. Everything else is still okay though. All right, that's kind of what's going on with holes. Now the vertical asymptote, does anyone remember what the vertical asymptote would have been for this one without actually putting the graph on there? Go ahead. It would have been +1, right? This is the one that doesn't cancel. So the vertical asymptote is the one that doesn't cancel, and it's going to remain a problem for the entire graph. The graph is actually then kind of revolved around that one area, that one idea. Okay, it's kind of around that one thought. All right, so that's something to just kind of think about because it's going to be very, very important as we move on with these things. Make sure that you understand what does and does not cancel, because if you just straight up cancel something out, it's going to make an issue as you go through the entire process. Because if you cancel something, you're basically saying it doesn't exist anymore, it's not an issue. It is an issue at the beginning of the problem. So we have to find a way to show that it's an issue, but continue on with the rest of the problem anyway. Vertical asymptotes do not cancel, which means they remain an issue for the entire problem, regardless of what you do. Okay? Any questions on those at all? These ones I think are the two that people are okay figuring out. And I'm going to write all this down again in a second, but I want to make sure that we have this conversation. Does anyone think that they know why horizontal or diagonal asymptotes exist? Anyone think they got that one? Go ahead.
For diagonal, I think it was the exponents, like the leading exponent on the numerator was greater than the one.
So what Olivia is saying is if it was a diagonal asymptote, the degree on top would have been higher than the degree on bottom. For a horizontal asymptote, the degree on bottom would have been higher than the degree on top. Okay? So the way that you can figure that out is not by looking at the factored form, it's by looking at the unfactored form. So I'm going to write all this stuff down so that we can have it in the same spot. So if I'm looking for, if you are looking for holes, you use the factored form, and you, I guess the way that you do that is by the things that cancel. So if you're looking at the factored form, the holes are determined by the things that cancel, or I guess would cancel, because we don't actually cancel them. It's just the things that would potentially cancel in the future. Okay? So if you're looking for holes, use the factored form. If you're looking for vertical asymptotes, you again use the factored form. And these are the factors that don't cancel. I'm also going to put in the denominator. Because the top is okay to equal 0, the bottom is not okay to equal 0. Okay? So if you're looking for holes or vertical asymptotes, you look at the factored form. That's the straightforward way of saying it. Now the tough part is if they don't give you the factored form, you have to find the factored form, right? And that's the part that's going to be a little bit trickier. If you are looking for horizontal asymptotes or diagonal asymptotes, you kind of look at it the same way. So horizontal, you look at the equation, the original equation, the unfactored equation, and you look at the highest degree. Okay. If you're looking for the horizontal asymptote, you are looking for the highest degree, wherever that is. If the highest degree is on top, that's great. If the highest degree is on bottom, that's great, but that will determine whether it's going to be horizontal or diagonal. Okay. So if you're looking at the unfactored equation, if I guess I'm going to say it like this. Horizontal asymptote is where the highest degree is in denominator. 99% of the time, it's when the highest degree is in the denominator, and that means that the horizontal asymptote will be 0. If the highest degree is in the denominator, that means that the the highest degrees in the denominator, the horizontal asymptote will be 0. Now there is one other case that it could be with horizontal, is if degrees in the top and bottom are the same, look at the coefficients. And we'll go through an example of this so you can see it. So if the degree is, if the degree in the top and the bottom are equal to each other, then you look at the coefficients. Okay? So those are the two cases for horizontal. If the top and the bottom are the degrees are the same, you look at the highest coefficient, and that will tell you what the the horizontal asymptote is. Okay, and then the very, very last thing is diagonal, and this is everyone's least favorite because it uses long division, and quite frankly, it just sucks. For diagonal, you look at the unfactored form. So for diagonal, you look at the unfactored equation, and then this is when the degree on top is higher. And this is everyone's favorite, use polynomial long division. This is something that we already learned one time, and everyone's like, oh, this is awesome. Everyone loved it. Everyone's favorite part of Algebra 2.
Was it when we were offline?
I don't know, were we online then?
Yeah.
Were we?
I don't even
So
remember.
we need to know long division.
You do.
Yeah,
That was the worst, honestly. I think I failed every long division problem. 'Cause I just,
I think I only made you guys do like 1 or 2 of them.
yeah, and I failed both.
Yeah.
Just not that. I don't think
All right, let's look at an equation and we can start to kind of figure out what's going on through these things. So that we can try to figure out what's happening and we can try to figure out what the equations look like and yada, yada, yada. So I'm actually going to take one off of the sheet so you can kind of recall it, I guess, because it might be a little bit easier. So let's say that we have the equation y equals 3x squared plus 21x plus 30 over x squared plus 4x minus 5. Now, the way that your book does this, your book goes through a whole bunch of like the A, B, H, and K things again, like we had talked about a long, long time ago. Remember when we talked about A's, B's, H's, and K's, and one is a vertical flip, one is a translation, whatever, one is a up, down, shrink, stretch, whatever it is. I'm not going to deal with that because your calculator is going to give you all of that information anyway, and I'm not going to force you to do that. These are the types of questions where I'm just going to ask you what like the critical values are, the critical things, what's happening at certain points, where the asymptotes are located, so on and so forth. And I think this is much easier to do by hand than it is to do via a graph. Because a lot of times with graph, you're leading on your estimations and whatever. You can still use your calculator to confirm whether or not you have errors on a table or whatever. But this to me is just one of the ways that you can do it by hand and it makes a lot more sense. If your book or quiz or whatever asks you to graph, type it into your calculator and put down the picture that you see on your calculator. I'm not going to make you do the whole translation thing, okay? I just don't think it makes any sense. So the unfactored form of this, or the factored form of this turned into 3 times x plus 5 times x plus 2 all over x plus 5 times x minus 1. Now, right now, you should be able to pick out certain things that are happening, okay? We should be able to pick out certain things that are happening. Very, very quickly, you should be able to identify the vertical asymptotes in the holes. That's what you should be able to do very, very quickly. Okay, so if you need to, you should be able to figure that out very, very quickly. I'm just looking for the holes. I'm looking for the factors that do cancel, or I guess they would cancel. So right there, x plus 5 tells me that there is a hole at x plus 5 equals 0. So what does x have to equal for that to be an issue? It has to be -5. So that tells me that there's going to be a hole at x equals -5. Okay, now remember, this is all without a calculator. This is all stuff that factoring is something you know how to do. Being able to factor it out and whatever you need to do should be pretty quick and pretty easy. The vertical asymptote is the one that doesn't cancel. So that is x equals the opposite of whatever's inside the parentheses. Right? That's all we use the factored form for. That's what we use the factored form for. We don't use the unfactored form for any, or the factored form for anything else past this. That's all we use it for. It tells us the issues. It tells us where my numbers aren't going to work. So now, this is the last one, and this is probably the trickier one. I'm trying to figure out if there is a horizontal or if there is a diagonal. And that is all determined from the highest degree in either the top or the bottom. You figure out where the highest degree is. Now in this case, the highest degree is equal in the top and equal in the bottom, right? So the highest degree is equal in the top and equal in the bottom. So I'm going to compare these two things right here. Okay? So when I'm looking at horizontal asymptotes or vertical or diagonal asymptotes, I'm looking to see my highest degree. And in this case, the highest degree is 2 in the top and it's in the bottom. So the two cases for horizontal asymptote were if the degree is in the bottom or if the degrees are the same, it's going to be horizontal. For diagonal, it was if the degree in the top is bigger than the degree in the bottom. So this means there will be no diagonal asymptote. It doesn't exist. So there is no diagonal asymptote because the degrees are the same. Remember, with horizontal, it was either degrees are the same or degree in the bottom. With diagonal, it was degree in the top. Right? So now if we look at this, we should be able to figure out our horizontal asymptote. And the way that you look at that is this coefficient over this coefficient. So 3 over 1 tells me the horizontal asymptote is 3. So I'm looking at the coefficients of the highest degrees. Okay, coefficients of the highest degrees. All right. This is really all it is. Look for the ones that cancel. Look for the ones that don't cancel. Look at the leading coefficients. Those are the three things that you really have to look for. And that's a lot easier to me looking at it in this form than it is on a calculator. Because once you get good at it, once you have it factored, it is just a recognition thing. That's all it is. You look at it, recognize what it is, write it down. So let's do one more. And I'll leave this one for you guys to kind of attempt. And it's actually going to be a diagonal one that we will lead into with polynomial long division probably tomorrow. So we have the equation y equals x to the third plus 5x squared minus 2x minus 24 all over x squared minus x minus 2. And the factored form of that is so try to find all of the critical values of these things, which means holes, vertical asymptotes, horizontal asymptotes, diagonal asymptotes. At this point, you should be able to figure out what's what. You should be able to figure out which one is which. You should be able to figure out whether it has a horizontal or a diagonal asymptote. Should be able to pick those things out at this point. All right, where are the holes? Holes are at 2. Where's the vertical asymptote? -1. Where's the horizontal asymptote? There isn't one. Anyone actually find the diagonal asymptote? So there would be a diagonal asymptote. The reason why this degree is higher than this degree. And the reason technically is, there is an x to the third term down here, right? 0x to the third. Technically there is. So if I have 1 over 0, 1 over 0 is undefined. So I can't say that there's a horizontal asymptote at 1 over 0. So since I can't say that, that means there's got to be a diagonal, and the way that we're going to set that up tomorrow is like this. So if you want to test yourself to see if you remember this, that's such a surprise. You're the first one I would have picked to say you were going to do it. So if you remember what you're looking at, that's what it is.
I don't think so.